Weight shift control for 2 Powerplants. For two-stroke engines, warming up is crucial due to the different expansion rates of metals when heated. Steel and aluminum components expand at different rates, posing challenges in two main areas. Firstly, in the cylinders, where steel walls expand more slowly than aluminum pistons. Rapid revving without proper warming can generate excessive heat, causing the piston to quickly expand and potentially seize in the cylinder, abruptly stopping the engine. The second concern is around the crankshaft area, where parts may become too loose with heat. If the engine heats too quickly, steel bearings in the aluminum crankcase can start spinning, potentially damaging the engine. To address this, a proper warm-up procedure is essential. Many two-stroke engines benefit from running at a set RPM for a specified duration. A typical warm-up might involve starting the engine at idle RPM, smoothly operating at 2,500 RPM for 2 minutes for initial warm-up, and then running at 3,000 RPM for 5 minutes. The cylinder head or coolant temperature must reach the manufacturer's recommended levels before takeoff. Cooling down the engine too much, especially during extended idling, can lead to potential issues during subsequent power applications. In water-cooled engines, prolonged idling during descent may cause the coolant to cool until the thermostat closes, leading to potential problems during sudden full throttle applications. Gradually adding power before descending prevents issues by allowing the thermostat to open gradually and warm up the radiator water. For four-stroke engines, warming up is also essential. These engines have a pressurized oil system that provides more uniform temperatures to components. Takeoff power can be applied once water, cylinder head temperature, CHT, oil temperatures, and oil pressure are within the manufacturer's recommended tolerances for power applications. Unlike two-stroke engines, four-stroke engines do not face the same issues with rapid temperature changes and can operate more uniformly after warming up. Continuing our exploration, gearboxes play a pivotal role in weight shift control aircraft, converting the high RPM output of an internal combustion engine into a slower and more useful RPM to turn the propeller. Various gear ratios are employed based on the engine's output speed and the required propeller turning speeds. Gearboxes directly bolt to the engine, with the propeller bolted directly to them. In two-stroke engines, the gearbox is kept lubricated with its reservoir of heavy gearbox oil, necessitating periodic changes due to wear and steel filings accumulation. Some gearboxes feature a built-in electric starter motor, facilitating engine cranking. For four-stroke engines, oil from the engine oil system is used for gearbox lubrication. Certain gearboxes may include a built-in centrifugal clutch, allowing two-stroke engines to idle at a lower speed without the load of the propeller, minimizing vibrations. The centrifugal clutch engages as the engine speeds up, smoothly starting the propeller, and disengages at idle, allowing smooth idling. The propeller, critical for thrust generation, utilizes engine power to rotate. Its design, with factors like airfoil shape, blade angle of attack, AOA, and engine RPM, influences the thrust produced. Weight shift control aircraft can be equipped with either fixed pitch or ground adjustable pitch propellers. Fixed pitch propellers have a set pitch by the manufacturer, while ground adjustable pitch propellers can be adjusted on the ground with hand tools. Induction systems bring in air from the atmosphere, mix it with fuel, and deliver the fuel or air mixture to the engine intake and cylinders for combustion. Two types of induction systems are used: carburetor systems, which mix fuel and air in the carburetor before entering the engine, and fuel injection systems, injecting fuel into the air just before entering each cylinder. Weight shift control aircraft predominantly use float-type carburetors, named after a float in the carburetor float chamber that maintains fuel levels. Modern carburetors operate with 3 separate jetting systems depending on engine power, supplying fuel or air mixtures through various jets during different throttle settings, ranging from idle to full throttle. Understanding the intricacies of gearboxes, propellers, and induction systems is essential for pilots operating weight shift control aircraft, ensuring optimal performance and safety during flight. In two-stroke engines, the carburetor settings initially configured by the manufacturer at sea level pressure pose challenges at higher altitudes. As altitude increases, the air density diminishes while the fuel density remains constant, creating a progressively richer mixture. This richness can result in engine roughness and power loss due to spark plug fouling from excess carbon buildup. To counter this, main jets are typically replaced with smaller ones, a modification based on the density altitude of the base airport. Operating from low-altitude airports and climbing to higher altitudes for short durations is generally acceptable. However, Configuring the jets for higher altitudes at a lower altitude airport may create a mixture that is too lean, risking engine overheating and potential seizure. 4-stroke engines, in contrast, often incorporate automatic mixture control for higher altitudes or a pilot-operated mixture control. Carburetor icing is a notable drawback of carburetor systems compared to fuel injection. It occurs due to fuel vaporization and decreased air pressure in the venturi, inducing a sharp temperature drop in the carburetor. This phenomenon can lead to ice formation, restricting the flow of the fuel or air mixture and reducing engine power. Carburetor ice is most likely when temperatures are below 70 degrees Fahrenheit and humidity is above 80%, but it can occur even at higher temperatures. The initial sign is a decrease in engine RPM, followed by engine roughness. To mitigate the effects of carburetor ice, some engines provide a carburetor heat option, either as an additional feature or constantly engaged in newer 4-stroke engines. While 2-stroke engines are generally less susceptible to icing, susceptibility varies based on specific installations. Pilots should consult the aircraft's PO for information on the probability of carburetor ice for the specific installation and corresponding procedures. In a fuel injection system, the fuel delivery differs from traditional carburetor systems. The fuel is injected either directly into the cylinders or just ahead of the intake valve. This system comprises key components such as an engine-driven fuel pump, fuel or air control unit, fuel manifold, fuel distributor, discharge nozzles, auxiliary fuel pump, and fuel pressure or flow indicators that illustrates a typical fuel injection system. The engine-driven fuel pump plays a crucial role by supplying fuel under pressure from the fuel tank to the fuel or air control unit. This control unit, essentially replacing the carburetor, regulates the fuel flow and directs it to the fuel manifold valve at a rate controlled by the throttle. Once at the fuel manifold valve, the fuel is evenly distributed to individual fuel discharge nozzles. These nozzles, located in each cylinder head, inject the fuel or air mixture precisely into each cylinder's intake port at the optimal time. Fuel injection systems offer several advantages. They eliminate the risk of carburetor icing and provide improved fuel flow, faster throttle response, precise control of the fuel-air mixture, better fuel distribution, and easier cold weather starts. However, there are some disadvantages to consider. Starting a hot engine can be challenging, and vapor locks may occur during ground operations on hot days. Restarting an engine that quits due to fuel starvation can pose problems.